Recorded. Okay, so we'll cover the third type of question that can be solved by dynamic programming, which is matrix chain multiplication problem. Okay, so it involves with the matrix multiplication problem again, but this time it is different from the matrix multiplication problem that we talked about before when we are in the divide and conquer chapter. So in the divide and conquer chapter, we are solving the problems of multiply two matrices together. Okay, and we found that a divide and conquer way can actually improve the running time efficiency of matrix multiplication problem using the Strasson's algorithm. Like we split the original problem into like 7 sub-problems. But this time the problem is different. It's matrix chain multiplication. It no longer deal with the problem of multiplying two matrices, but this time we have a chain of matrices together, and the problem is totally kind of a different problem here. So we'll see how dynamic programming can be applied because of the nature of the problem. We'll analyze the optimal substructure of the problem, like how do we obtain the optimal solution to the original one by kind of splitting the problem into sub-problems and find the optimal solutions to the sub-problems. Okay, so in that sense, the dynamic programming analogized to the divide and conquer approaches, but essentially they are two different algorithms. For DP, the biggest difference is that we have overlaps in the sub-problem space, and we want to avoid solving the same sub-problem for multiple times. We want to solve each sub-problem just for once, and after that we'll store the results. And later on, when we need to know the results of the same problem, we don't solve it, but we refer to some memory, external memory space, like a hash table or like a array list to look up the results. Okay, so previously in rod cutting problem and in Fibonacci problem, we use arrays to store the solutions to the smaller problems. And in this case, in the matrix chain multiplication, we'll use a two-dimensional data structure. You can think of it as a matrix or as a table. Anyway, it has two columns, row columns, and it has two dimensions, rows and columns. So you can use the row index and column index to locate the solution to the sub-problem that are of specific sizes. Okay, so in this case, in the matrix chain multiplication problem, the problem size is kind of not defined by just one number, but by the row index and the column index. It is defined by two integer numbers in general. Okay, so let's look at the problem. And it's actually a straightforward problem. So given a sequence or a chain of matrices, we want to multiply them together. Okay, so we want to compute the product A1 times A2 times AN. We have n input matrices, and the according to the convention or naming convention in linear algebra, we use capital letter A to indicate a matrix. And the matrix is a two-dimensional data structure. We have rows and columns, right? And we know that the linear algebra tells us that matrix multiplication is associative, which means we can we can add parentheses around any number of matrices. And no matter how we parenthesize the product equation, the equation will always yield the same products. Okay, so for example, if the goal is to compute the product by A1 times A2 times A3 times A4, we can basically, I listed 4 different ways of adding parentheses. The first row, if we look at it, the parentheses define the order of computation, right? In the first row, the most inner parenthesis is outside A3 and A4. That is the first layer. Okay, so this way of parenthesization means that we will compute the products of A3 times A4 first. Okay, because the results of multiplying 2 matrices together is another matrix, is also a matrix. Okay, so then the second computation is A2 times the results of A3 times A4. And then the third step is A1 times the results of this big chunk of matrix multiplication. Okay, so the different ways of parenthesizations basically define the order of computation. Okay, but no matter which way we organize the parentheses, the results will be the same. Okay, but you will see the different ways of parenthesization comes with different costs. Okay, so here we called a product of matrix is fully parenthesized if the whole expression is either a single matrix or the product of 2 fully parenthesized matrix products. Okay, so this is a bit a recursive way of definition. Okay, so all we need to know is that we can put parentheses around into different positions. Okay, and given a sequence of matrices, we will now look at how the different ways of parenthesization will lead to different costs in computation. Okay, so first of all, the 2 matrices A and B can only be multiplied if they are compatible. Okay, so it's a requirement that the number of columns in A must equal the number of rows in B. So that is the requirements of the matrix multiplication. Okay, and so now we assume that our input sequence satisfies that condition. Otherwise, the whole expression gonna be invalid. Okay, so if we interpret it with mathematical expressions, say the dimension of matrix A. Okay, here we have a little lowercase a, which is unnecessary. Okay, you can ignore this lowercase a. So the dimension of matrix capitalized A is P by Q, which means it has P rows and Q columns. Then in order to multiply A with B, then the B must have Q rows and R columns. So the number of column here must equals the number of rows in B. So that is the requirements if we want to compute A times B. So the result of multiply A and B together is another matrix, and we name it C. And the dimension of C is also determined by A and B, which is P by R, P rows and R columns. Okay, so now we can notice the property of C, that's the number of rows P is exactly the number of rows of A, and the number of columns R is exactly the number of columns in B, right? The P is the leftmost number in A, and R is the rightmost number in B. So we can, and the Q in the middle are eliminated. Okay, the Q, number of columns and number of rows here, they are eliminated in the final results. Okay, and that is quite easy to memorize, right? We only need to consider the leftmost number, which is the number of rows, and the rightmost number, which is the right of columns, to compute the dimension of the resulting matrix C. Okay, so this is an important property we will need to use in the case of matrix chain multiplication. So the A here is a typo here. I should have removed it. Yeah. So I probably want to say that the capital A is a P by Q matrix. Okay, that's what I probably want to say before. Okay, so that's one property we will need to use. Okay, so let's memorize. Let's review the implementation of matrix multiplication briefly for now. So we basically need a triple for loop to implement it. Okay, so given two matrices A and B as inputs, we will basically need to use 3 for loops to indicate the to compute the results of C. Okay, so the first for loop. So first of all, and this is a quite sensible implementation, because we check whether A and B are compatible, right? If not, then we say A and B cannot be multiplied together. And then we will record the number of rows in A as P, and the number of columns in A as Q, and the number of columns in B as R. So PQR are defined. And then we allocate some space, memory space, for the result C. So it must be a P by R matrix. Okay, so we'll look at how much computation will be needed in order to compute C. So it's a 3-layer for loop, right? The first for loop iterates over 1 to P. Okay, you can think of it as we iterate over the rows here. Okay, the i's iterates from row 1 to row P in the results matrix C. So this is the results C matrix, and the blue rectangle is A, and the orange rectangle is B. Okay, so we need to compute each entry in C. So that's why we need to iterate over the rows. And the second for loop iterates over the columns, which is 1 to R, right? So for each entry in C, say the element or the entry at the ith row and the jth column, we basically need to access the elements in A and B, okay? And this is where we need to use the quantity Q, because Q is the length of one row in A and one column in B, okay? Because the elements Cij, like lowercase c I j, is the result of the inner product or dot product between the ith row in A and the jth column in B. Okay, so that's why we need to iterate over all the elements in ith row. So this aik represents the ith row and kth element in A. And the bkj means the jth column, but kth row in element B. So, and k iterates over 1 to q. So that means we basically take all elements in A at the ith row and all elements in B in jth column and compute the inner product. And the inner product is actually the summation of all the components in each dimension. Okay, so that is the incantation. Actually, we have gone through this before when we introduced in the Divide and Conquer chapter, right? So here's just a briefly review. So what's costing us computation resource is a step here. We need to compute the multiplications between two numbers, aik and bkj, right? And we need to accumulate them together. Okay, so basically, how many scalar multiplications are needed is our major concern, right? That is where the where the actual computation happens. So of course, we want to first calculate how many times we need to do, and that the answer is also just straightforward, because the first layer for loop has p iterations, and the second for loop has r iterations, and the most inner for loop has q iterations. So it's straightforward to know that the number of scalar multiplications needed is p times q times r. Okay, so this statement will be executed for p times q times r that many times. Okay, so larger this quantity or these products means longer time the multiplying two matrices will take us. Okay, so we basically want to so if there are a sequence of matrix multiplications, we want to organize the matrix, the products in a reasonable way, so that the total cost of scalar multiplications are minimized. Okay, so we'll come to that in the next slide as well. Okay, so now we're gonna see how, given a sequence of matrices, how different ways of parenthesization will affect running time. Okay, so now we start from a very simple example. If we want to multiply three matrices, A1 times A2 times A3 together, okay, and we assume that A1 is 10 by 100 and A2 is 100 by 5, right? And A3 is 5 by 50. So first of all, let's check if they are compatible among each other, right? So A1 times A2, the number of columns matches the number of rows. And for the second, A2 times A3, the number of columns also matches the number of rows here. So they are compatible, so it's okay. We can put them together into a chain. So now let's look at the first way of parenthesization. So we can multiply A1 and A2 together and multiply the result with A3. So let's look at how many scalar multiplications will be needed. Okay, and because the dimensions for A1 is 10 times 100, and the dimension for A2 is 100 times 5. So according to the formula in the previous slide, do you remember that? It is P times Q times R, right? So the number of scalar multiplication for computing A1 times A2 is 10 times 100 times 5, which is 5,000. Okay. And the resulting matrix is 10 by 5. And that is some intermediate results, which we will need to use to multiply with A3, right? Okay, so that's the first step. And then the next step, we are multiplying a matrix of 10 by 5 with a matrix of 5 by 50. So again, the total number of scalar multiplications is 10 times 5 times 50, right? Which is 2,500. So, and now we are done. So in total, there are 7,500 scalar number multiplications needed. Okay, so that is the cost for parenthesizing A1 with A2. Okay, so now let's look at the second way, which is parenthesizing A2 and A3 first. Okay, so let's look at examine the results real quick. Okay, so because the dimension of A2 is 100 by 5 and A3 is 5 by 50, so the total number of scalar multiplications by the formula of P times Q times R is 25,000, which is already greater than the first solution, right? And also the resulting matrix is 100 by 50. Okay, we'll need to use that resulting matrix to times with A1. And that step, the second step, requires even more computations. It's 10 times 100 times 50, which is 50,000 computations. So in total, it's 75,000, which is 10 times more computation time needed just doing the same task, right? We're doing the same task, but with different ways of parenthesization. So this is a huge gap in performance, and we definitely want to choose the first way because it is much, much faster, okay? Okay, so hopefully this example shows the necessity of solving the matrix chain multiplication problem. Okay, so given the matrix chain multiplication equation or expression, we want to parentheses them in a way that the number of scalar multiplications is minimized. Okay, so this is a important task, and it is not an easy way to solve it, but we'll start from some easy thinking, just like the way we did for rod cutting, we'll see if any brute force solutions exist first. Okay. So here's a more formal definition of the problem. Okay. Okay. So the definition, so the more formalized problem is like, given n matrices from A1 to AN, and we know the dimensions for each matrix AI. Okay. So for AI, we use the dimension P subscript I minus 1 and PI to indicate the dimension for matrix AI. Okay, so we want to parenthesize the products. Okay, so that's the total number of scalar multiplications is minimized. Okay, so a brute force way is just to exhaustively check all possible parenthesizations. Right. So given a sequence like this, like we can first think of the last layer of parenthesization, right? How do you want the last layer of parentheses to be, or the last layer of multiplication? Like we can put a parenthesis around A1, right? And parentheses around A2 and the rest of the matrices. So that is one way, okay? And we can put around A1 and A2, right? And the rest of the parentheses, okay? So the blue arrows here indicate the last layer of parenthesization that we want to place, okay? So these, given this input sequence that has 10 matrices, it's already 9 possible choices, right? But that's just for the last layer, okay? So we can use Pn, the capitalized P, to indicate the number of possible parenthesizations for a chain of n matrices, okay? And we can see that we can use a recursive definition to indicates the results, indicates the solution, right? Because the last layer has 9 possible positions, right? So the solution to P10 is actually P1 times P9 plus P2 times P8 plus P3 times P7, blah, blah, until P9 times P1. Actually, if I switch the order, it will be easier to understand, right? So this is a recursive solution to the number, to the question of how much Pn will be, okay? And from our intuition, we'll see that the P must be a very big number, because this is a very, very bushy recursion trees. There's a lot of recursion calls going on, right? P1, P9, all of these expressions are recursive calls, okay? So if we generalize it into the case of 9, then we can express this kind of a recurrence equation into this form, right? We need to, this summation sigma actually iterates over all possible positions for the last iteration, for the last parenthesization. So it's pk times pn minus k. So k is the length on the left, and n minus k is the length on the right. So if we solve this recurrence equation, it's gonna be some function that is even higher, even going faster than the exponential function, okay? Which is super inefficient, okay? And if we want to go through that many possible ways of parenthesizations, it's gonna take us too long. So, and we will find that there are actually a lot of overlaps in the resulting subproblems, okay? So we're gonna solve this problem using a dynamic programming approach. Okay, so as we mentioned in the previous class, in order to solve a problem with dynamic programming approach, we need to first check if the problem represents some property called optimal substructure. And optimal substructure is just a fancy way to say that, okay, this problem, in order to solve the original problem, we need to obtain some optimal solutions to the subproblems. Okay, so let's see if we can find such a pattern, such as optimal substructure in this matrix chain multiplication problem. Okay, so now we can use some new notations. This A with subscript I to J to indicate the resulting matrix. Okay, so this whole expression is a matrix from the product of AI times AI plus 1 to AJ from these little small segments within the original problem. Okay, so let's say we use this notation to denote the product, the results of the products, and the J is larger than I. Okay, and so in order to parentheses the products, we must split the chain between AK and AK plus 1 for some integer K. So that is, give me a second. Excuse me for a minute. I need to fix the printer under my desk. Okay, I'll be back in a few minutes. Thank you. Okay, sorry, apologize for that. Yeah, so in order to solve this, to parenthesize this chain product from AI to AJ, we need to choose a point. Let's say that point is K, and K must be between I and J. It must be greater than I and smaller than J. Okay, so and that is actual the last the placements where we place the last layer of parentheses for this subproblem, for this subchain from AI to AJ. Okay, so K is something between I and J. We must determine. Okay, and we can rewrite the subproblems from AI to AK, use the same notation, use the subscripts from I to K, right? And the second subproblem on the right to be using this notation of A subscripts K plus 1 to J, right? Because the index, the subscripts start from K plus 1 to J, right? And the index from on the left is from I to K, right? So that is the notation, follow the same rules. Okay, so we can represent the total costs of computing the products between AI to AJ, represented by the cost of computing the left subchain from AI to AK, plus the costs of the right subchain from K plus 1 to J, and some cost of multiplying the resulting two matrices together. Because the results on the left is a matrix, and the results of the right chain is also a matrix. In order to multiply these two matrices together, there also needs to come some cost in terms of the scalar number multiplications. Okay, so so far this equation looks pretty much like the a divide and conquer thinking, right? It's like we substitute, we split the original problem into two parts, into two subproblems, and we need to solve them like individually and then combine the results. Okay, so this is also the so-called optimal substructure. But in a way, we'll eventually we'll find that we don't need to use a recursive way to solve it, because there's too much overlap in terms of subproblems. There's too much overlap in the subproblem space. Okay, so now we consider what this part would be. Oops, sorry. What's the cost of multiplying the results together? Okay, so because the results of the left chain from AI to K has the dimension of Pi minus 1 times Pk, right? This is the what we can obtain by looking at the leftmost side matrix and the rightmost side matrix, right? So for the left chain, the leftmost matrix is AI and the rightmost is AK. And the results will only be, the dimension of the results is only determined by these two, right? All the dimensions in the middle, they are eliminated by the rule of matrix multiplication, right? So we will know that the dimension for AI to K is Pi minus 1 by times Pk. And also for the right chain, the dimension can also be expressed by Pk, which is the number of rows of AK plus 1, and the Pj, which is the number of columns of Aj. Okay, so we know the dimensions for these two matrices, and so we can know the cost of multiplying the two matrices is Pi minus 1 times Pk times Pj. So this is exactly the quantity of P times Q times R, right? In order to obtain the multiplications between these two matrices. Okay, so we can write this expression, write the cost of multiplying the resulting two matrices by this expression. Okay, and then we can further formularize the problem. Okay, so suppose the optimally parenthesized chain from AI to AJ. In order to obtain the optimal parenthesization, we need to split the product between AK and the AK plus 1. And within this optimal solution, the left chain from AI to AK and the right chain from AK plus 1 to AJ, they both need to be optimally parenthesized. Okay, so in order to obtain the optimal solution of the bigger one, we need to optimally parenthesize each of the subchains. Okay, so we basically split into two subproblems, the left chain and the right chain. And we need to basically consider all possible values of k, because we need to choose the one that returns the optimal results, which is the minimal cost. Okay, so assume that, so okay, so we next we're gonna excuse me, we're gonna use some shortened notations to indicate the results of the optimal solutions to this matrix chain subproblem, matrix chain problem. Okay, so we can assume that we have some arbitrary function or magical function called dp. Okay, it's a magic procedure that knows the optimal solution, which is the minimal number of multiplications for any sequences. Okay, so we can write it in this way. The dp of this input chain from A1 to A5 is the minimum among a bunch of choices. Okay, I'll write these choices down. The first way is parenthesize A1 and then parenthesize A2 to A5. Okay, and plus the cost of multiplying the two results, right? Which is P0 times P1 times P5. Okay, and the second choice is multiplying A1 and A2, and the right part is A3 to A5. And then the cost of multiplying the two results, which is P0 times P2 times P5. Okay, and the rest of the choices are something you can infer yourself, because we are basically defining choices by the last position, by the position of the last layer of parenthesization. Okay, and now let's look at these subproblems again. Okay, so as input as the example, we can look at dp from A2 to A5. And this subproblem is also the minimum among a bunch of choices, which is first multiply parenthesize A2 and parenthesize A3 to A5, plus the cost of multiplying the two results, P1 times P2 times P5, right? And the second choice is parenthesize A2 and A3. And the third choice, and the third choice is parenthesize A2 times A3 times A4. Okay. Okay. And if you look at the problem here, the second subproblem, which is the dp of A3, thus A3 to A5, it's also a minimum choice among two options, which is A3, parenthesize A3 and parenthesize A4 to A5, or A3 to A4 and then A5. Okay, so hopefully, so now we are expand the subproblems into even smaller subproblems. But now we can notice one fact is that look at the highlighted subproblems. The subproblem of from A3 to A5 is solved once here, but it's solved again here. And the subproblem from A4 to A5 is solved here, but it's solved again here, right? So the same subproblem is solved over and over again, for multiple times, and that is something we don't want to see, right? Something we should avoid by memorizing the results, right? So after the optimal solution of A4 times A5 is solved, we should not solve it again here, right? And after A3 to A5 solved here, this one should not be expanded. We just need to read the cost immediately from the stored results. Okay. So this shows the properties of why dynamic programming can be used here. Okay. So now we're gonna simplify our notations step by step, okay, until we reach some points that we can use some very simple data structure to represent to store the solutions, okay. So we can write the notation dp of something from A1 to A5, because dp is some imaginary concept. It's just a solution. It's just to indicate the solution. Okay, we use a magical symbol to indicate the solution. So, and the input is a sequence. Okay, so we can just use the starting index 1 and 5 to indicate this whole expression, right? So in the next slide, we can rewrite the dp of ai to aj, use some simplified index using just the starting index I and the ending index j. Okay, so it's the dp of a comma j to indicate the whole complex expression here. Okay, so we basically rewrite the previous expansions. So the dp from 1 to 5 is the minimum amount dp11 plus dp25 plus the additional cost of multiplying the two resulting matrices together, which is P0 times P1 times P5, okay? So this is actually the same thing, but rewrite with a simplified notation, okay? And we'll soon observe that why do we need to use dp, right? Because dp is an imaginary function that takes two integer numbers as inputs. So it's just has the same property as a 2D array, right? So the solution of some problem is actually an element in the 2D array, which can be represented by another even shorter name, which is m of ij. Okay, so writing this way is totally equivalent to writing the solution into dp of something, right? It's just an element in the 2D array. Okay, so we can do the further simplification, right? We just write the whole part on the left with the new notation on the left. So M indicates the solution to the problem from A1 to A5 is the minimum among 4 choices, which is M11 to M25, M12 plus M35, M15, M13 to M45, and so on. Okay, so we basically rewrite the thing on the left with this much more compact form to the right, right? And even to be simpler, using simpler expressions, we can rewrite M15 to the minimum amount 1k plus k plus 1 to 5, and the additional cost, which is P0 times Pk and P5. And the k actually ranges from 1 to 4, because k needs to be greater or equal to 1 and smaller than 5. Okay, because k is the last is the possible positions to place the last thing parenthesization. Okay, so this is the very compact forms. And to put it into a more general case, right? Because we
Yeah.
Yes.
And the other one didn't.
Hello? Yeah, can you repeat your sentence? I cannot hear you. It's some noise. Or if you can type your question, if it's if possible. Okay. So if we write it in a more general form, instead of in concrete numbers 1 and 5, we can use I and J. Then it's the same thing actually. We let K iterates from I to J, right? We need to compute the summation between MIK plus MK plus 1J plus the additional costs, right? And we need to choose the K that minimize the whole expression, right? So that is the solution to the subproblem from I to J. All right, so given this framing, different way to frame the problem, we can use some external memory space, like 2D dimensional, 2D array to implement the solutions of this dynamic programming approach. Okay. So before that, let's consider a recursive solution. Okay. So if we let it use some recursive ways, and this is basically the recursive recurrence equations that we are using, right? So we use Mij to indicate the minimal number of the multiplications for the subproblem from I to J. Then we can write the equation in this bigger equation. And this algorithm, if we use recursive calls, it will run in exponential time, right? Which is no better than the brute force method, okay? Because all the subproblems are solved repeatedly. We already seen that. If we solve them recursively, then it's a terrible choice. So basically, we want to use a dynamic programming approach, okay? So we'll start from a bottom-up dynamic programming solution, okay? So basically, let's look at the problem more closely again, because given the inputs from 1 to n, the subproblem, any subproblem defined by I and J must be bounded by 1 and n, right? And the total number of distinct subproblem is the quantity of choosing 2 distinct elements among n elements, right? So this expression is the number of combinations, right? N choose 2. So, and we want to solve that many distinct subproblems without repeating, right? We don't want to solve the same problem for more than once, okay? So we want to solve each subproblem just once, okay? And a straightforward solution is to solve the smallest problem first, because the bigger problems rely on the smaller problems. And we know that because we choosing 2 elements among n as boundaries for the subchains, the smallest subproblem will be of size 2, right? So that is the smallest subproblem, and the size n is the biggest subproblem. So let's see, for the smallest case, for the subproblem of size 2, we can look at the range of I and J, right? You can imagine a sliding window of 2 that slide to the left 1, to the right n, to get all possible subproblems of size 2. then in that case, the subproblems are A1 times A2, A2 times A3, A3 times A4, and so on until AN minus 1 to AN. Okay, so in this case, if you look at the range of I, it ranges from 1 to N minus 1. And the range of 2 is from 2 to N. That is for the smallest subproblem. And if we increase the problem size again by 1, say the subproblem of size 3, then we will have A1 times A2 times A3, A2 times A3 times A4, right? And then, of course, we can see that the I will range from 1 to N minus 2. And the J will range from 3 to N. Okay, so we can use the size of the subproblem to decide the range of the left index and the right index. Okay, and we can use these quantities to help implement the algorithms because we want to solve the smallest subproblems first. Okay. All right, so we can imagine a sliding window of width L, okay? And then we need to solve the smallest subproblem first. And L ranges from 2 to N, okay? So let's quickly look at this matrix chain order procedure, okay? So this procedure takes the P index, the P array as inputs. Okay, so the P is the array that stores the dimensions for all the matrices in the chain. Okay, so it stores the the dimension for A1, which is P0 and the P1, right? And the dimension for A2, which is P1 and P2. Okay. Okay, so let's look at the procedure first quickly, okay? It will initialize two matrices, which is M and S, okay? So M has n rows from row 1 to row n, and n columns from row 1 to row n. And the S has one less row and one less column, which is from row 1 to n minus 1 and the row 2 to row n. So we'll see why we need this. So it's okay if we don't directly to immediately see the Y behind the S matrix, okay? And the M's will be initialized to 0. Okay, actually the diagonal elements in matrix M, the ith row and the ith column will be initialized to 0. Okay, so there are 3 layers of for loop here. The first for loop, it actually goes over all possible subproblems. Okay, because the L, so actually I'm indicating the first for loop L from 2 to n here. Okay, because we know that all the subproblems must range from 2 to n in terms of its size. And the second for loop is for iterating over the left, the range of the left index. It must be from 1 to n minus L plus 1, because that is the range of the left index. We already seen that in the previous slide that the left range will be determined by the size L, right? So if L is 1, if L is 2, then this quantity is n minus 1, right? If L is 3, then this quantity is n minus 2. And also, the J will be determined by I and L, right? Because J is L minus elements to the right of J, to the right of I, okay? Okay, so that is the first two for loops go over all possible subproblems. And for each subproblem, we need to solve it, right? Because the subproblem is from I to J, and we need to solve it by go through all possible ways of dividing the subproblem, right? So there are that many places to place, that many positions to place the last layer of segment of parenthesization for this particular subproblem. We need to place K among I to J minus 1, okay? So, and for each K, we will look up the values in the M matrix to look at whether it's solved or not, okay? So by the time we solve the subproblem from I to J, any smaller subproblems, such as from I to K and the K plus 1 to J, they are already solved because we start from the smallest subproblem 2 first. Okay, so in the smallest case, we will refer to M, for example, M11, M22, but these values are initialized to 0. So these are all already known values. Okay, and we basically find the smallest solution to this subproblem from I to J, use this for the third for loop, and we'll store the results for this problem into the two-dimensional array M, and also the solutions where the positions to place the last layer of parenthesization. Okay, so and in the next class, we'll go through a simple examples of this procedure. And here, we just need to realize that, okay, this is a pretty good implementation because it's just three for loops. Although it's not ideal, but it's much better than the exponential time algorithm. It's much more efficient than the brute force way or the pure recursive solutions. So yeah, we'll end here, and this Thursday we'll continue the rest parts of this matrix chain order procedure, and we'll talk about a top-down method for the matrix chain multiplication problem too. Okay, so I think there were students. How do I pronounce the name? Florenda. Do you have a question? If you want to raise it here, or do you mind if you type it? Anyway, so I hope you all consider like if you have any suggestions for the course or any kind of general feedback about the course delivery, you can just let me know, and I'll do my best to make adjustments and to accommodate your needs. Okay, and I will release the video, publish the video, and release the quiz questions later today. All right, thank you for coming. Bye-bye.